Our last speaker for this session is Dikun. Dikun got his BSc and Master's degrees in Geophysics from China University of Geosciences in 2005 and 2008. He's just, somewhat recently finished a PhD at UBC in 2014. He's now a postdoc at the UBC GEF, working on electromagnetic modelling and inversions.
Thank you, Brandon. Hi, good afternoon, everyone. Yeah, so today I'm just going to talk about a case study, but on a slightly different topic. It's on groundwater application. So we use the Airborne EM technique to map groundwater salinity. Yeah, so just a brief outline. So starting with the background at this site called Bookpurnong in South Australia. And then we talk about two Airborne EM surveys. One is SkyTime 2006, another one is Resolve 2008. Then we talk about how we invert those Airborne EM data to map the distribution of groundwater intrusion, salty water intrusion. That's the conclusion. So the location of this site is in South Australia. So you can see on the map here, South Australia, this is Adelaide, and it's just on the border of South Australia, and I think it's, I can't remember, Victoria, yeah. And there is a zoom in here, there's a Murray River, with lots of floodplain. And there's a little orange box here highlights an area called Bookpurnong irrigation area. So the airborne survey is actually just within this orange box. So this is our survey area, and with digital elevation. So for most part, it's just so flat. It's average elevation just 10 to 15 meters, not much topography. But on the right-hand side, there's a highland where the farming is happening. So they irrigate over the highland. But over the floodplain, it's just nothing, just some vegetation, just river and maybe some beach, and nothing happening there. So the hydrological model at Bookpurnong is, this is probably kind of complicated, but the basic idea is we have irrigation on the highland. So there are going to be lots of water recharging the local groundwater. So there's a little bit bump on the water table on the highland. Then there's a hydraulic gradient from the highland to the river. So there's going to be a lot of water flow from highland to the floodplain and bringing some naturally occurring brine from deep reservoir to the river and causing the floodplain becoming more salinized. So the problem is vegetation are dying, so this is a big concern for local government. Yeah, so this is a big picture motivation here. So to help understand what's happening there, so there's some hydrological concept we need to introduce here. So the basic question is whether Murray River is losing or gaining water. So there are two concepts here. First one on the left-hand side is called the losing stream. In this case, the water level in the river is higher than the water table on the bank. So in this case, water actually flow from the river to the bank. Basically, the river is losing water, so it's called a losing stream. Because the fresh water in the river, so the river will be electrically more resistive. On the right-hand side, it's called the gaining river, which is the reverse. So the ground table on the bank is higher than the river, so the sea line water is actually recharging the river, so making a more conductive river. So this is a very basic, simplified concept here. As a geophysicist, we need to do some survey, so it's very important to know if there's any physical property that we can distinguish. So of course, the people did some groundwater sampling. This is a very small scale groundwater sampling from the shallow wells. So you can see from January 2006, yeah, we have most of the groundwater very salty. Along the left-hand side, this is close to the river, so the transect is going from the river outwards, so it's more fresh, shallow, and close to the river. And once it's getting inland or also going to deep, it's just more conductive. So just an explanation of the color bar here. So the basic green is 1 centimeters per meter, 2, 3, 5, 4, 5. Red is basically just 5 centimeters per meter. So from March 2007, they did another sampling. So there's a variation. It looks different, exact same transit, but just longer. And again, so just the same ballpark. So what we can observe here is the geological structure is pretty layered, or maybe at least it's quasi-layered. And the conductivity compared to your like a mining environment is much higher. So the average is like maybe 1 centimeters per meter. That's very conductive. So this is groundwater sample. So in reality, it must be a mix of groundwater, gravel, sand, kind of different stuff. So this maybe give us a reasonable estimate for the upper bound of the conductivity. Like average conductivity could be maybe like 10 centimeters per meter or something. And again, we see the seasonal variation. Like this is well, 1 year apart. So lots of changes in terms of conductivity. So just bear those things in mind. Then 2 surveys. First one, frequency domain, which is a result 2008. 5 frequencies for horizontal coplanar, 1 frequency for vertical coaxial. And the time domain survey is done by SkyTime 2006. This is a dual moment system. So for high moment, 24 time channels, where it's 47, they did 8,000 microseconds. And we also have a low moment, use much lower like transmitter moment, but only 20 time channels, but much earlier time channel, 12 microseconds. So this is basic geometry, like the transmitter receivers at the tail of the frame. So the survey is survey area, basically 3 by 7 kilometers, like 100 meter line spacing. Because of the 2 high moment, low moment in SkyTime, essentially we have 3 different data sets: the resolve, frequency domain, and the LM for low moment, HM for high moment. So basically we're dealing with 3 data sets. This is just an overview of the data for the resolve at 2 different frequencies and the in phase and the quadrature in ppm. You can kind of see, because it's pretty flat, you can kind of see the river by tracing the dark blue, right? And the same thing for SkyTime. On the top, low moment, bottom, high moment. On the left, early time channel. On the right, late time channel. Yeah, again, you can kind of pick up the river from just from the data. So that's good. But again, this is just data. It's not conductivity. So also we need depth resolution. So we need to do some inversion. So just one quick slide about our inversion algorithm, not too complicated. So for the modeling, as I said, this is a 1D environment. So what we do is do 1D layered Earth modeling. So we eventually may do 3D, but for the first pass, we do 1D. So for the inversion code is EM1D FM, UVC code, frequency domain code. Then for the time domain data, we use EM1D TM, which is essentially EM1D TM plus inverse Fourier transform and convolution with waveform. So many of you guys here may have used this code. And for the inverse modeling, we minimize this object functional, which is a 5D data misfit. We just measure how the size of the difference between the predict data and the model data. And this little one is a standard deviation or like uncertainty in the data. At the same time, we want to minimize the structure in the model. So in one model, basically just want the model as simple as possible. This is the L2 norm here. So just to draw attention to a little gap here called MREF. So this is something we use as a reference modeling or inversion. Basically what it says is whatever we build in the structure, we build structure in the model, we all build upon the foundation of the reference model. So a reference model essentially is a soft constraint in the inversion, which is able to guide the inversion to a particular direction. So you have a slope here as a background or reference, and you just find a finer scale structure based on that slope. So this is just give you like a general guidance in the inversion. So the first round, this is a very simple one. So first we need to check for self-inconsistency in the data set. So we have to make sure data are modeled correctly. There's nothing wrong. We understand the data correctly. The normalization, the primary field, or unit, all kind of stuff. So we have to at least make sure we can get individual soundings converted to reasonable models. We don't get like a 1,000 centimeters, something like that. And also have to identify some obvious outliers, so make sure they're not making trouble for us. For example, I pick one particular sounding here and do the inversion. So this is a recovery model, looks kind of reasonable from 0 to 1 kilometers. Everything looks fine. And look at date fit. So look at number here. On the top right is resolved date fit. So the total misfit equal 1, good. And on the bottom, this is the sky time, blue for low moment, red for high moment, circle for observed data, and the star for the predict data. So the thing is, we notice that for low moment, we have a really large misfit, 3. We can't get this number smaller than 3. So ideally, we want 1 for our target misfit. So there must be something wrong in the low moment data. Yeah, so we identified for the first time channel, it's always really difficult to fit. So yeah, so I think we just simply remove the earliest time channel in low moment data. And also, if you pay attention to resolved data, so the highest frequency, 130 kilohertz, is kind of problematic across whole survey. So it's also very difficult to fit. So in this case, we'll also remove all the highest frequency from the entire data set for the resolved data set. So this is just first step. So remove this one, remove this one. And so the next round, which I usually call it, sometimes the people call it a blind inversion, but I think the word blind is a little bit negative. So here we call it the free range inversion, which is much more positive. So, which means right? Everyone like free range, right? It's more expensive. So essentially you let the inversion run freely. So that's why it's called free range inversion. So the idea is here we have a minimal intervention. We don't do anything fancy. We just let it go and see what happens. So here we use a uniform background model, like a 0.1 sims per meter, which kind of like a lower bound of the average in this area, and now 35%. See what happens. So at the same sounding location, this is our data fit. So for the resolve, because we removed the first highest frequency, so now we only have 5 frequencies. They're all good. So all the misfits are down to 1 unit. That's perfect. And yeah, seems like everything is nicely fit. This is our recovery model. Okay, so this is interesting. They're different. So you can see they all recover some sort of a conductive layer, but they're kind of in the different thickness, different depths. So the annoying thing is that for the high moment data, it requires a huge conductive layer on the top. But the resolve and the low moment are kind of agree very well. So this part is very annoying. Then if we take a close look at the data fit for skytime data, missing? Yeah, so so for the earliest time channel in low moment, at high moment, they're underfit. So I think this could be something like we have seen in the Airborne EM inversion, like because for the early time channels, the primary field is not totally zero in practice, but in the modeling we use the theoretical waveform, which assumes the primary field is zero. So there could be like a discrepancy here. So we can never fit those data just because we're using essentially different waveform. So this is what we have learned here. So why different models? Well, of course, first reason, we're doing inversions. There's non-uniqueness in the inversion. Could be like, there might be a unified model, but just we couldn't find it just because they have different sensitivity in different systems. The second reason, there might be system-specific errors or bias. For example, like I just said, for the earliest time channel, you never know what your real waveform is. You only have a theoretical waveform. And in this case, it could be a change of ground truth, because remember the seasonal variation. So over a year, because this is a very shallow groundwater, so everything can change. And the resolve and the sky time may just be varying different conductive models. So, solutions. So first one, we can do joint inversion in theory, so which essentially put all the data in the same sensitivity matrix. Unfortunately, the time domain, frequency domain data are inverted by different code. So currently we don't have such code to do the time domain, frequency domain simultaneously. That's reality. Eventually maybe we have such code, but right now I don't. Then the next thing you can do is called a cooperative inversion. So for this topic, refer to you to a paper written by my colleague, Mike McMillan. In this paper, he described a strategy that essentially, so let's say you have two datasets, A and B, and you invert A dataset for one iteration and grab the model to feed the second inversion and do another iteration and take the model back to the first one, then do this back and forth. So eventually, you were able to arrive at the final model, satisfy both datasets. That's the basic idea. So by the way, this is the best paper in geophysics in 2014, so it's a very well-written paper. But we have 3 datasets here, and there are possibly more datasets coming. So we need to deal with this complication. But there might be systematic errors, maybe systematic errors in resolve, systematic errors in high moment, systematic errors in low moment. They're basically using different waveforms. So that kind of complication, maybe there is just no such unified model that fits all dataset. And for this environmental application, there might be change of ground truth. So basically, finding one unique model that fits everything is just impossible. That's why we do this grid to discrete inversion. So the basic idea is, so each sounding is treated as a single jurisdiction. So each sounding can develop its own model. Basically, resolve has its own model, high moment has its own model, low moment has its own model. But after each iteration, there will be a congress. During the congress, they meet together. What they do, each jurisdiction submits a proposal for model update. So they, okay, I want model look like that. Then another jurisdiction comes in, oh, I want model look like that. So eventually, we need to play democracy. So they vote for a common reference model. So the idea is that after the meeting, they take the common reference model home and do the next iteration. So make sure their next proposal is more similar to the common reference model. So the idea here is we can maximize the unification, but at the same time, we still honor individual data set or allow the discrepancy in the model. This is just basic idea. So same sounding, do the agree to disagree inversion, ATD inversion. So just some statistics, summarizing the data misfit, all converge to 1 after 8 iterations. The state fit, exact same sounding, basically fit pretty well. And this is the resulting model. So the dashed line is the final common reference model. So you can actually see the improvement here. So the amplitude is still different, but at least we have a kind of thickness and the depth kind of more aligned, right? But they're still different, and the noising is still here. The high moment data still requires thick conductor layer on the top. This is bad, so we need to fix this. So as I have said, the early time channel is still underfit. I think it's possibly just non-zero transmitter current. So we just go ahead, remove the first 6 time channels from high moment, maybe it's the first 4 time channels from low moment. And same sounding, try it again. Again, data are fit. Looks much nicer here. Here's the final model. So basically they are kind of overlapping. Just summarize what I did for the 3 rounds for the same sounding. Free range, it's just all over the place. ATD inversion, but minimum intervention, only remove some outliers. So much better. It's big improvement, but still different. Then we remove some like early time channels, which I think is associated with a system bias. They arrive like perfectly. So this looks great. So all great product all comes with a fine print. So there's something I need to discuss. So there's a trade-off between minimum intervention and bias removal. So eventually, if you keep removing time channels, you eventually only have 1 time channel from the airborne soundings, or like you can always fit they find the common mode. That's very easy, but you are losing a whole bunch of information. So there is a trade-off here. So you don't want to do this too aggressively. And there must be a lateral continuity in this removal. So for example, remove the 6 first time channels from this sounding. You want to kind of keep same numbers for the next sounding, right? You don't want to move to the next sounding and remove 20 time channels. And it's kind of challenging or something like issues here as to how to decouple the system bias and the change of ground truth for, because at some point it's not very easy to distinguish the two because they're all showed up in the model as discrepancy. Okay, so this is just yeah. So on the plan view, so what I just showed was just some single sounding. So here I'm showing you a plan view for the whole survey area. On the top, on the connectivity on the surface. On the bottom, 20 meters below the surface, and on the left, resolve. In the middle, low moment. On the right, high moment. It's just free range inversion, so they're just not the same, and it's very difficult to draw a concrete conclusion from those images. And on the plan view, after ATD inversion, on the surface, they're much more closer, and on the bottom, they're kind of basically, if I go back and forth between the free range, agree to disagree, you see the improvement, right? And essentially, they are fitting the data almost to the same degree. So this shows we are able to achieve kind of the same, bring different data set together to form like a more unified model, but still keep a lot of discrepancy in the model. So that's next interesting question is, okay, so actually you can see the difference between this image and this image. Right? This is redder, this is more red, this is kind of like a lighter. So what I do is I do the difference between this one and this one. This is the result. This is the result minus high moment on the surface, result minus high moment 20 meters deep. So those are discrepancies in the model that cannot be easily removed by just getting rid of time channels. They are always there. And also if you compare this with just a result model and some other like flat lines, some features, we just can't find this pattern to be in correlation with any known feature. For example, infrastructure, power line, something. I was trying to explain this by something else. For example, maybe the altimeter is not working very well along the path, but it's not along the along the flat line, So the only reasonable explanation I have for now is this is just because of the change of the ground conductivity. That's the only thing so far I can tell. So if this is true, basically we're able to map the temporal variation of the ground conductivity using this kind of technology. Yeah, so just conclusion, it's almost time. So we're using Airborne EM to solve groundwater problem in Australia. Some practical challenges. First, we have a 3 data set. They give different models, so which is confusing. And there's no such joint inversion code. We have to use whatever we have right now. And there might be system bias or errors in model in the data, so we have to deal with multiple models. There could be seasonal variation. And we developed a agree to disagree strategy here. So we allowed each data set to have its own model. So the information is exchanged through a common reference model. So maximum unification, but we still allow discrepancy. We make sure data are fit. So there's a question for, this is still ongoing research, how we want to decouple the system bias and change the ground truth for this particular problem. And if you're looking into the future, so eventually what we can do is we will allow each datum has its own model, not just one soundness model. Or each one-time channel has its own model, or even models. Each time channel can have multiple models, maybe starting from different starting model, maybe starting from different depth weighting, maybe starting from very different initial conditions. So that would be something very interesting. So just extra stuff, we sent CSRO for a dataset, and also this case history is archived on an online initiative called EMGSI. So please visit this site. So, and this is actually a collaborative online, like open source EM case study database. So yeah, just talk to Doug or Lindsay if you want to learn more. Thank you.
Thanks, Dikun. I think we're going to have to update Sheriff's Geophysical Dictionary with a few of those new terms.
Time for one question?
Time for one question, Ken.
Democracy is messy.
Yeah.
What about the SkyTEM inversion, and I assume the Geoscience Australia inversion? Did they see the similar, where did they fit in this space? You use the codes you're familiar with, but I'm very sure at least one or both of those other solutions were applied to these data sets. At least the SkyTEM did. And have you looked at that?
Which code?
Well, the Art House guys always run SkyTEM.
Oh, yeah.
With their...
Well, yeah, that's something I didn't bring up here, because I think we got better results. That's something I didn't want to mention.
Well, then you get bragging rights, but you got to show it.
Yeah, because they invert both high and low moment together, don't they?
Huh?
The SkyTEM, the others software inverts both high and low moment data.
Yeah, according to their publications, yes. Yeah. But there are still some issues or something I don't quite understand. Yeah.
Did you try using EM 1DTM to invert both high and low moments together?
No, because the high moment, low moment are using different waveform. So
There's an approximation to the ramp plot that you can use that allows multiple ramps that works with SkyTEM. And there's also just an extended waveform.
well, yeah, because basically high moment, low moment are not just different in terms of ramp. It's also different in terms of on-time part. So it's kind of like I don't know. I could try, but I didn't do that. It's just unknown. Yeah.
Okay, well, so just follow up with Dikun in the break. Just want to join me in thanking all the speakers this afternoon.